let's get going. So in the previous lectures, we spoke about rotation, analogous variables to translational motion. We spoke about relating the linear and rotational variables, kinetic energy, how to calculate the rotational energy, and we spoke about torque. Okay. Today, we're going to be talking about Newton's second law again and work again. So, let's see if we manage to finish or not. It's all up in the air at the moment. So, Newton's second law for rotation. First thing first, who remembers what is Newton's second law just for translational motion? Excellent. It was simply F equals ma. Can you tell me what you think the rotational analog of it would be? We have worked on translation for the last 2 lectures, translating rotational and translational variables into one another. What do you think its translation, literal translation, is going to be? Okay, F equals mv squared over r, one person. Well, we know torque is equal to FTR. We know F is equal to ma, so torque is equal to MAR. We also know that tangential acceleration is equal to alpha r. We put that back in, we get m alpha r r, which means we have mr squared alpha. And what is mr squared? Simply I. So translation, as we said from before, torque is the angular equivalent of force, inertia is the angular equivalent of mass, and alpha is the angular equivalent of acceleration. Okay. We end up with torque net equals I alpha, which is very, very similar to F equals ma. Write that down because we're going to be doing a sample problem on it now. Okay. Now, in judo or karate or taekwondo, there is a very signature move on how to throw someone. And you don't just grab someone and pull them over. You hold them, you go down a bit, and then you pull them over to throw them. And it's called a judo hip throw. Now, to throw an 80-kilogram opponent with a basic judo hip throw, you intend to pull his uniform, because that's what you're holding onto, the clothes, with a force F and a moment arm D1 equals 0.3 meters. From a pivot point on your right hip. You wish to rotate that person about the pivot point with an angular acceleration of alpha equals -6 radians per second squared, and that is clockwise. Assume that the rotational inertia relative to that pivot point is 15 kilograms meter squared. So we don't really need to do any calculations with inertia. They are given it as 15 kilograms meter squared. What must the magnitude of F be if before you throw him, you bend your opponent forward to bring his center of mass to your hip? So both of the center of masses are the same, are on the same location, which means also that all the calculations for torques will be from the same point. Well, let's write our items down. Force, moment arm, center of mass, and FG. These are the forces that are happening. My moment arm, this is 30 centimeters, so 0.3 meters. My I is 15 kilograms, and my alpha is this. What is my F needing to be? Well, we know my torque is equal to I alpha, and we also know that torque equals R cross F. So RF equals I alpha. We put in the numbers, and we end up with 300 newtons. Okay. Okay. Now let's change something. This time, your opponent is not being very, stop moving. This time, your opponent is not being very helpful. And the center of masses don't align. So instead, when you pull your opponent refuses to budge, and he's still standing straight. Well, now you have an issue because of this. This orange line means there's an extra point. Okay, your center of mass is at a different point to your opponent's center of mass. So your moment arms are different. So we have the same inputs, but now we also have another D, which is D2. The gravitational force on the opponent is different. So what happens is you have your gravity, which is trying to pull your friend this way, but you are trying to pull that way. So you have total opposing forces or torques. Same, but now my torque is not only dF, it's also d2 mg. And I need to put in about double the amount of force. Okay. وين راحت الماينس؟ الماينس the question asked for the magnitude of F. Otherwise, it would be minus 300 newtons. Okay. Otherwise, it's a minus 300 newtons. Okay. Let's try doing it a bit of a different way. A mass hanging from the end of a horizontal bar, which pivots about an axis passing through its center. So this is a pivot point. Okay, كان في مسمار هنا. But it being held stationary. The bar is released and begins to rotate. As the bar rotates from the horizontal to the vertical, what is the magnitude of the torque on the bar? Does it increase? Does it decrease? Or is the magnitude of the torque on the bar constant? And then part B is, as it goes from horizontal to vertical, what about the angular acceleration? Does it increase or decrease? Decrease, decrease. Both of them decreases, okay. A, B. A whole bunch of A's and B's, no C's. Well, we have said that torque equals R cross F, which is the same as saying RF sine theta, correct? Now this is my R, and my R is, when it comes here, this is still my R, but whereas my angle here was 90 degrees, here it's less than 90 degrees. My force is down, mg, at all times. So given that my angle decreases, I start with sine 90. Sine 90 is 1. Okay, sine 90 is 1, and my angle decreases. So sine theta is also going to decrease. Up until this becomes just like this. When it becomes like this, your angle is 0, and your torque also becomes 0. So the correct answer is decreases. As the bar rotates, the magnitude of the angular acceleration of the bar. So we know T equals I alpha, and I is constant. Alpha equals torque over I. As my torque decreases, my alpha is also going to decrease. Good. Let's do another problem. It's always nice to do some problems to understand. So we have one of these axles. Okay. Yep. Figure 10-19A shows a uniform disk with mass m equals 2.5 kilograms. So now my disk itself is heavy. It has 2.5 kilogram mass. Remember in the previous chapters, whenever we had a rope and a pulley, we always said, consider them to be of negligible mass or massless or very light pulley. But here it's different. It's actually heavy enough. It's 2.5 kilograms. And a radius of 20 centimeters, mounted on a fixed horizontal axle. A block with mass m equals 1.2 kilograms hangs from a massless cord that is wrapped around the rim of the disk. Find the acceleration of the falling block, the angular acceleration of the disk, and the tension in the cord. So we want to know A, alpha, and tension. Okay, the cord does not slip and there is no friction at the axle. So we only need to worry about gravity and tension. That's it. Well, we know A equals alpha R. We write down that R equals 20 centimeters, M equals 2.5 kilogram, M equals 1.2 kg. We need to find T, A, and alpha. From our handy dandy list of moments of inertia, we know that the I of the disk is half mr squared. Let's get started. Gravity down, tension up. T minus mg equals ma. Now here I have chosen to write minus a because I am taking up to be positive and down to be negative. You don't need to follow this convention when you do it yourself. Okay, remember that from the previous chapters. Now, on top of that, the rotating disk also has some forces on it. Tension of the rope is what's pulling on the disk, on the pulley, and the radius R is your moment arm. and torque equals I alpha. So torque equals, so torque half mr squared minus alpha, since it's going in a clockwise direction, is equal to R cross. We also know that torque equals RF. So R and my force is tension. What is tension? Well, which one, Mariam? Which bit? Well, we know torque equals R cross F. We know torque equals I alpha. So RF equals I alpha. My arm, moment arm, is the radius. So R. My force is the tension going downwards. So minus tension. It's equal to, my I is here, half mr squared. And my alpha, I don't know what it is, but I know that the pulley is going in a clockwise direction. And we said that clockwise is negative, anti-clockwise is positive. So minus alpha. Now R cancels with R. So we end up with T, and minus cancels with minus. So T equals half mr alpha. We also know that AT equals alpha R. So alpha equals A over R. Half MA. Okay. Now, Ryan is asking, where did the mg go? The mg is already involved in this A. Because we're saying this is the net acceleration. The net acceleration is determined by this combination. T minus mg equals ma or minus ma. Okay, so you have three different things that you're bringing together. First, you're doing T minus mg equals ma. This is just translational motion. Then you are doing torque, RF equals I alpha. And then you're using them both together. So this is what my acceleration actually is. When I rearrange this equation, this is what my acceleration is. Now, once I put in these numbers in, what I will get will be the tension will be equal to 6 newtons وين في G.
هنا دكتور لما حصلنا ال A.
صحيح موجود. It's here also. Look. هنا تحت.
بس أنا قصدي إنه في الإكويجن اللي من يعني derived، فوين راحت ال MG عشان بعدين هي تواجدت في ال A.
ال MG متضمنة في ال A، فهنا لما نحن نقول T equals half MA قصدش صح؟ half m g 2m على m plus 2m. هذا هو الفاينل equation. Okay, slightly confusing. We are bringing in everything we have done so far in the previous 9 chapters or 10 chapters into one problem here. Forces, torques, rotations, everything is coming into one equation. Okay, let's do a simpler example. A mass M hangs from string wrapped around a pulley of radius r. The pulley has a moment of inertia I, and its pivot is frictionless. Because of gravity, the mass falls and the pulley rotates. The magnitude of the torque on this pulley is what? Is it greater than mgr, less than mgr, or equal to mgr? I'm going to do it with you here now on paper. There's a hint. Is the tension on the string equals mg or not? Let's see. Equal, less, equal, less, grade, mgh minus r. Okay. Let's do it together. What is my force here? What is my F net? mg minus t. Okay, I have chosen that down is positive, up is negative. So mg minus t. And this is equal to ma, which means my acceleration will be mg minus t over m. Torque equals rf, rma, rm, mg minus t over m. M and m cancel out. We have mg r minus rt, which means it is less than mgr. Okay. كيف عرفنا إيش؟ Because mgr minus something is less than mgr. X minus something will always be less than x alone, right? So mgr minus rt has to be less than mgr. Now one might say, but what if r is negative? Well, radius cannot be negative. What about t is negative? But you have already taken t is negative here. So you have already taken that into account. If t is equal to mg, then you will not have a rotation. You will not have a torque. Because remember, the whole reason you have a torque is because you have a force pulling it down and causing it to go in a circle. But if down is mg and up is mg, then your net force is 0, which means you don't have a force, which means it doesn't go around, so you don't have a torque. Okay? All right. Let's try another one. This one is a bit more difficult. A mass m is attached to a long massless rod. The mass is closed, so we don't consider the mass of the rod. Okay? The mass is close to one end of the rod. Is it easier to balance the rod on end with the mass near the top or near the bottom? So if it's down here and I push it a little bit to one side, and if it's up here and I push it a little bit to one side, which one will be more stable? Okay, we have very good opinions on both sides. Let's see. When you're going through an angle, you're including a torque, right? Where do you measure your torque from? Your R. You usually put it through the center of mass, right? where is the center of mass of this system? Now, this question is a bit tricky because it tells you the long rod is massless. So if I assume that the center of mass is here in the middle, it would make no difference if it's at the top or the bottom. But that is not quite correct, because there is an obvious point, okay, here that we cannot measure it from the center of the object because it's on a table. So when it rotates, it's going to be rotating about the table itself. So this is going to be my 0 point. Now, if I do the same angle, same small angle, let's say, for example, 5 degrees. Okay, tiny angle. Here, my torque is going to be RF sine 5 degrees. My F is going to be given by this. It's going to be mg sine theta. Right? So R mg sine 5 degrees sine 5 degrees. The same 5 degrees up here on top, okay, will have a much bigger R because this distance is way bigger than this distance. So again, I will have big R, mg sine 5. But since your R is more, you're going to have more torque, which means it will tend to move more. So it's more stable, aka it's easier to balance the rod with the mass near the bottom. Okay, and you can try it out. If you have a pencil or something, you can put a small rubber here on top and try to topple it. Okay. We spoke about torque. We spoke about kinetic energy in rotation. Now I have a question. What about work? How do I define work in terms of a rotational thing? We know that kinetic energy is final. Delta K is Kf minus Ki. And if I'm looking at the change in kinetic energy, it's still going to be Kf minus Ki. But the question is, how do I calculate K aslan in the first place? In translational motion, it was half mvf squared minus half mvi squared. But in rotational motion, as we have discussed multiple times before, the tangential velocity v depends on where you are on your object. So not a very useful component. We will need to translate this into something that is consistent for the entire body, aka rotational variables. What do you think the translation of this would be? M goes to I, as usual. V goes to omega, and you end up with half I omega squared minus half I omega I squared equal to work. Simple. So let's take three things. We have a sphere, a hoop, and a cylinder. All same M, all same R, and they're all rolling along with exact same speed V. Which has the most kinetic energy? A, B, C. Well, K equals half I omega squared. Omega equals VR. Or is it V equals R omega? Can someone remind me, please? V equals R omega. Which means omega equals V over R. So half I V over R all squared. Now, since all of them have the same V and the same R, all of them will have this component the same. It all comes down to I. النصات بتروح مع النصات. So, it all depends on the moment of inertia. Sphere has 2/5 mr squared, disk has half mr squared, and hoop has a full mr squared. So the hoop wins. It has the most kinetic energy. How do we do work? We know work is equal to F dx. We translate F torque x theta. Done. Okay, these translations are really, really easy and really, really important. So the way I do it, as I have said before, okay, I don't memorize these. I have never memorized these. I know these and I translate them on the go. It depends on the type of question, Dina, but in your formula sheet, you have all the I's, so you can choose it from there, if it's not given in the question. Work is equal to torque and then the change in angle, just like it used to be F delta X. What about power? We had said that power is the rate of change of work, dW by dt. And since it was FD, it became FV. Now we do it again, we translate. F becomes torque, V becomes omega. Now I will add one more slide here, which I think this is really, really important. It's a summary from your book, which I think is really, really good and important. Okay, so these are going to be really, really good summaries. Theta, x, omega, v, alpha, t, and their relationships. Translational equations, rotational equations. So I will also write the way I have been doing it so far. So v equals u plus at, s equals ut plus half at squared, and v squared equals u squared plus 2as. You can keep x naught here, and the first one stays. Okay. Finally, in translation you have m, in rotational you have moment of inertia, mi/ri squared. Translational you have kinetic energy half mv squared, rotational is half I omega squared. F equals ma, torque equals I alpha. F dot ds, torque d theta. And P is FV, P is torque omega. Okay, these three slides really summarize everything we have done in chapter 10. Okay. Let's take a 5-minute break. Yes.
ممكن تفتح سلايدات الليكتشر الماضي، عندي سؤال لو سمحت.
Okay, towards the end of this lecture, or actually since we have just finished chapter 10, let's answer a question on chapter. What was it? Lecture 22, صح?
Yeah.
Yeah, which slide?
I don't have the number. Maybe 15. No,
This one?
there is. It was a question 16. So.
هذا؟
Yes.
Okay.
دكتور مثلا لو هالسؤال احنا عرفنا ان الماس is equal، بس لو الماس مال two الأوبجكتس ما equal وش نسوي عشان نحدد the center of mass؟
إذا ما equal,
ايه.
you put the other mass in one of them.
What?
So say for example this is m and this is 2m مثلا.
Yes.
Okay.
كيف نحدد the center؟
I'll show you. You want to find what the center of mass is, or you want to find what the inertia at the center of mass is?
أول شيء نحدد the center عشان نحدد الإنرشيا.
If you want to know what the center of mass is, okay, you go 1 over m, sum of mi, ri. Right? I will still take this position to be 0, 0. Say this is 1m, this is 2m مثلا. So I have 1 over m plus 2m, sum of m times L over 2 plus 2m times L over 2. I will end up with 1 over 3m, ml over 2 plus ml, which is equal to 3 ml over 2 and 1 over 3m out here. M will go with m, 3 will go with 3, and you will just end up with half. Okay, half L, sorry. So this will be your center of mass, L/2.
Okay, Dr.
Okay, and you don't actually need to find the center of mass first to find inertia. We can find inertia directly. So inertia is sum of mi Ri squared, صح? Now
Yes.
the only rule for R, this R does not need to be RCOM. It just needs to be the same for all the particles. Okay, so again, I will take this to be the 0. Okay, so I will have m times L/2 plus, sorry, m L/2 squared plus 2m L/2 again squared. This I will end up with ml squared over 2 plus 2ml squared over, sorry, ml squared over 4. 2 squared is 4. And 2ml squared over 4, which is equal to 3ml squared over 4.
Okay, thank you.
Okay, so this tells me that my inertia at the center of mass, okay, is 3ml squared over 4. Actually, no, you are correct. Let me think of it again.
دكتور احنا في الشابتر الماضي عشان نحدد السنتر لازم كنا نطبق هالرول، فعشان أول شيء عشان نطبق يعني عشان نعرف السنتر فنطبق هالرول اللي هي x center of mass اللي هي مال الانتجريشن، وبعدين نحدد الأوبجكت، فهنا نفس الموضوع.
انك اول شيء you find the x center of mass and then do this calculation is absolutely correct. I'm just trying to figure out if I can just use this directly from a point that I assume. Let me try it out. 3 over 4 L all squared plus 2m L over 4 squared. So this will give me 9ml squared over 16 plus 2m L squared over 16. 9 plus 2 is 11 over 16. Yep, you are correct. I am wrong. I cannot use all of this. My bad. My bad. I will get this, which would be 11 over 16 ml squared.
Thank you.
Okay. Now, amazingly, if I do 11 over 16 ml squared, which is around this point, plus mh squared, so 3m because 1 and 2m, yeah, m, and the h here between them is L over 4. I will end up with 11 over 16 ml squared plus 3m L squared over 16. 11 plus 3 is
14.
14 over 16. Okay, so even then, even then, this works. Okay, so we find around center of mass plus mh squared, and we find it at this point if we want to. But why? Just use CMM. من وين جبت 3L over 4? Well, because the whole rod is L, half of it is L over 2, half of the half is L over 2.
L over 4 دكتور.
Sorry, L over 4. فلما أجي هنا أحط 3 over 4L because it's the distance from here to the center of mass here. And then from here to here is just L over 4.
مريم لأنه تغير يعني السنتر مال الماس.
The location of the center of mass changed. It's no longer in the center. It's a bit to the right because this is twice as heavy. Okay. Let's continue. اوكي خلص شرحنا البتاع في ال5 دقائق. Okay, we only have 10 more minutes or 12 more minutes in the lecture anyway. So soon enough, you'll get rid of me. Okay. So far, we have spoken about translation and we have spoken about rotation. We still haven't spoken about one of the most basic things that we see every day, something like a football moving. When a football moves, it doesn't move like this. It doesn't move like this. It actually rotates while it's moving translationally. So it does both of them together. Now, when translation and rotation are combined together, we call it rolling. يتدحرج. Okay? We know theta is equal to S over R, which is a radian measure. I'll just differentiate. Okay, I'll say S equals R theta and differentiate. And I get V equals R omega. Again, we did this before. Okay, but this is a reminder of what theta is and what V is. And let's take a look. Pure rotation, pure translation. And if I have both of them together, then I have what I call a rolling motion. Some funny things happen in physics when we go to rolling motion. Now, if I look at something that is rolling like this, okay, my velocity of the center of mass and my center of mass, by definition, go in a straight line, the orange line. But if I put a red dot here somewhere, okay, red paint, and trace it while it's moving, okay, I will end up with these arches, okay? Now, how much do I move? Suddenly, the answer to this question is not very clear, because how much do I move where? Bear with me, I know it sounds weird. If I am looking at the center point of each wheel, then going from here to here, how much did I move? This distance x or s. In time t, S over T is T center of mass. Simple. So far, everyone is okay with this? Okay, good. But if I choose this point P down here, okay, and I have moved from here to here, this point P would have moved through this red direction, right? How much is this? This will be theta multiplied by the radius. Okay. So what's going on? Write these down because we're going to use them in the next lecture, in the next slide. For VCOM, it's S over T, and it's the same as omega R. And our S is equal to theta R. Yes, Noor. So we spoke about translation alone and rotation alone. This chapter, we bring translation and rotation together. This is the same wheel, Rayan. It just moved from one place to the next. It's exactly the same wheel. It moved via rotation from this point to this point. Okay. Now let's take a look at the velocity. Okay. By the way, how many people here are interested in photography? Just taking photos of stuff, moving stuff. No one? Only taking photos of food? Okay. Those who are interested in photography will find this bit quite interesting. Okay. Now we have agreed that VCOM is equal to S over T, right? So the velocity of the center point here is S over T, and here again is S over T. Okay. Now, this point P, when it's down here, its velocity is in the opposite direction to the movement because it's going in a circle. It's going that side. So its velocity is minus VCOM in pure rotation. And up there, it's plus VCOM. Okay, so far so good. بعد مفهوم. In pure translation, okay, if I'm only moving this way without rotation, then everywhere has the exact same velocity. VCOM, 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 all in this direction. Still so far so good. Now, when I am doing both rotation and translation, like a car wheel, for example, what do I end up with? My center is still VCOM. At the bottom, minus VCOM plus VCOM end up with a velocity of 0. And at the top, VCOM plus VCOM is equal to 2 VCOM. It appears as if that when we are rolling, one object has 3 different velocities. The bottom part has a velocity 0. The center of mass is a velocity v. And the top part has a velocity twice that of the center of mass. What is the effect of this? One effect of this is when you take a really fancy camera and you snap a photo of something that is moving. Okay. Look at how sharp the photo is here versus here versus here. What can you notice? Anything? Okay, one person said the same. Here's what happens. You have your camera. You click on the thing. Shutter opens and closes. And it takes a certain amount of light in. You end up with a photo that looks like this when something is moving. And some people use really, really big lenses. And you end up with this. This is a much clearer photo of the effect that happens. Okay, and this is not only on professional cameras, like even when you take a photo of a bird, or for example, of anything moving, of a little child that is, well, children usually, well, actually little children do rotate most of the time, but anyway. Okay, what do you notice about this photo? You will notice this seems to be in perfect focus. You can see each one of these lines, spokes, very clearly. In the center, you can still see some effects. At the top, you cannot see any of the spokes. Nothing. Empty. And the reason is that at the top, it's going at 2 VCOM. At the bottom, it's going at 0, and this is at VCOM. So when you're trying to take a photo, your shutter can only focus on one of these things. At what speed would you like me to focus? Something that is not moving, something that is moving a little bit, something that's moving much faster. Yeah. And you would think that, okay, the solution to this is easy. I am simply going to change the settings so that the shutter opens for enough time to capture 2 VCOM, and then the whole wheel will be equally sharp. Okay. Yes, Rayan, for center 1. Okay, so V equals 0, V tangential. V tangential equal VCOM. V tangential equals 2 VCOM. So you're like, okay, I'll set it. Oops. I'll set it to this. وخلص الموضوع. Not really, because what's going to happen is you are going to end up overexposing your other parts of the photo, and they will not be clear either. So when something is rotating, it's very difficult to get all of it in focus at once. Okay? If you don't believe me, the next time you put or fan on your ceiling, just take a look at it. Okay, Dina, tell me, what have you not understood? Yes, that too, Rayan. Which one, Dina? Okay. Let's take a look at something that is only rotating, nothing else. Okay. What is the velocity at each point? Well, the center is not moving at all because it's only rotating in place. not going anywhere. So the center is not going anywhere. So velocity at the center is equal to 0. At the top, the rotation is going this way, so the velocity is VCOM. Right-hand side, it's still VCOM, but in this direction. Bottom, it's minus VCOM. Left side, it's VCOM. And we're assuming the rotation is going in this direction. So far, so good? Good. Now let's take a look at pure translation. Forget about A. Forget about A. Let's go to B. Okay. Let's assume, yes, it is equal to R omega. Yes. Vcom equals R omega. Yes. Okay. Now let's look at pure translation, nothing else. So now it's moving like this. Not rotating and moving. No, just moving like this. No rotation. If something is moving like this, every single point at it is going to be moving at exactly the same velocity at the same time, right? So all of them are VCOM in the same direction, the same number. This okay? So we have agreed this is okay. Is pure translation also okay? Okay. Now let's look at rotation. At rolling. What is rolling? Rolling is something that is moving and at the same time rotating. Okay, like a ball or a wheel. Now, assuming that we have fixed the COM somehow, we have chosen it so that the VCOM of translation and VCOM of rotation is exactly the same. Okay? But when they're happening at the same time, we add up the velocities. Simple, yes? But velocities are vectors, so they have directions. So plus and plus, we end up with 2 VCOM. 0 and VCOM, we end up with VCOM. And the bottom side, here we had it going in this direction with velocity something. Here we're having in this direction with VCOM. Minus and plus of the same number is equal to 0. So we end up with something that is rolling, that it appears as if each part of it is moving at a different velocity. Okay, last slide. A circular hoop rolls without slipping on a flat horizontal surface. And you will see this sentence over and over again, without slipping. Why? Because this only makes this calculation where we add the two, this only works if this part at the bottom does not slip. Okay, if it slips, then you have an extra velocity there. So to make things simple, we will keep things without slipping. A circular hoop rolls without slipping on a flat horizontal surface. Which one of the following must be true? All points on the rim of the hoop have the same speed. All points on the rim of the hoop have the same velocity. Every point on the rim of the wheel has a different velocity. Okay, so we all agree that this is not possible. Everyone says every point on the rim of the wheel has a different velocity. And no one says all points on the rim of the hoop have the same speed. I will agree with you that every point on the rim has a different velocity. They can have the same speed, but it's not necessary. Okay. Well, this is the end of today's lecture.